You're listening to the FQXi Podcast. Today, the microscopic laws of physics are reversible, yet we experience an irreversible flow of time. Why?
Our experiment actually was designed to visualize with an optical system what the model of the irreversibility within the constructor theory framework could essentially reconcile what is microscopic time reversal laws of quantum mechanics with what is always present in classical physics in the macroscopic world, that is irreversibility.
Quantum physicists Fabrizio Piacentini and Knoll describe their experiment investigating a possible explanation coming from constructor theory.
With these two quantities is that we can evaluate if the constructor qualifies, or if the quantum homogenizer qualifies as a constructor for performing the task in one way and in the other.
I'm Zia Morali. Hello and welcome to the podcast from the Foundational Questions Institute. This is the third in our special series on irreversibility produced by reporter Logan Chipkin and physicist Chiara Marletto of Oxford University. Back in April, we ran Logan's conversation with Chiara and Vladko Vedral, also at Oxford, in which they described constructor theory, a relatively new meta-theory that sets out new laws which should encompass all other physical theories. Constructor theory reformulates physics in terms of the operation of constructors that transform things from one state to another, like a kettle that boils water, and the kinds of operations that are allowed. Marletto and Vedral spoke mainly about the theory, including puzzles surrounding irreversibility and time. What's strange is that at the microscopic quantum level, processes are equally likely to occur forwards or backwards. But in everyday life, we know that time only ever marches forward. So how does that irreversibility emerge? Marletto and Vedral had touched on an experiment that was carried out to test one of constructor theory's predictions about how this happens by demonstrating that certain tasks at the quantum level can be carried out in one direction but not in reverse. If you haven't listened to that episode, trust me, go back and do so now and then come back. There's a link to it on the podcast page, fqxi.org/community/podcast. In this episode, Logan picks up the story with experimental physicists Fabrizio Piacentini and Knoll of INRIM, the Italian National Metrology Institute in Turin. They discuss this recent experiment, which they performed, testing whether or not a constructor theoretic notion of irreversibility is compatible with time-reversible symmetric laws. Spoiler alert, it is. In particular, they discussed using a quantum homogenizer to test quantum theory's compatibility with constructor theory's expression of irreversibility. It's a bit of a mouthful. Over to Logan.
Okay, I'm here with Fabrizio and Laura to discuss your recent experiment on constructor theoretic irreversibility on a quantum system. But before we get into that, could you two please introduce yourselves?
My name is Knoll. I am a postdoc student here at Italy. I'm actually from Argentina, and I've been working for the past 2 years here with the group at INRIM in Torino.
For what concerns me, I'm Fabrizio Piacentini. I'm a permanent researcher here at INRIM, that is the Italian Metrological Institute. I work on experimental quantum optics applied to quantum metrology, quantum information, and quantum foundations research. Together with Laura, built up the experiment and the data analysis and everything. So we're the ones that essentially put our hands on the optical table and the instrumentation.
I definitely want to get into that. So I spoke with Vlatko and Chiara about a lot of the theory behind the experiment that we're going to discuss. But just to review some of the background, could you tell me what exactly your experiment was designed to test?
Our experiment actually was designed to visualize with an optical system what the model of the irreversibility within the constructor theory framework could essentially reconcile what is microscopic time reversal laws of quantum mechanics with what is always present in classical physics in the macroscopic world, that is irreversibility. You perfectly know if you open a box with some gas particles in it, the gas particles will spontaneously fill the room, but it's impossible for them to spontaneously re-enter this box, essentially. This is an example of irreversibility. That's in apparent contrast with the time reversal laws of quantum mechanics, because if you deal with quantum objects, transformations can be seen from on one direction temporal side and in the other one as well. You have a complete reversibility unless you make something on the state, you make something on the particle, you act on it, and you make it collapse. But it's something different. If you leave it by itself, then all transformations are unitary and all transformations are time reversible.
Laura, following on that, your experiment focused on a quantum system to test the constructor theoretic understanding of irreversibility. So what is the actual toy model that you used, and what tasks did you try to show were in fact irreversible?
Okay, so our toy model consists basically on a quantum homogenization machine, which can be thought of as a machine that works like a thermalizer. That's to say, you have a system and you have a reservoir. What we use as toy model is basically how the system eventually tends to thermalize with the rest of the reservoir, let's say. We use as our, let's say, quantum resource, single particles, which are photons. So we use them basically to encode the information. We have a photon, which will be our system, and we use three other photons that represent basically the bath or the reservoir, which interacts with our main system, performing this thermalization process.
And the gate that the operation that allows to do that is the so-called partial swap. That is a swap between qubits that is not deterministic. I mean, there is a certain probability that the swap happens and a certain probability that it doesn't. Of course, we have n qubits, n photons in this case, in the reservoir, in the homogenization machine, on the homogenizer, as you want to call it. And your substrate qubit, your particle under test, goes in the interaction with this homogenization machine, and qubit by qubit undergoes a partial swap. Even if the partial swap probability is small, just like some adiabatic process, and maybe you have in theory n qubits with n arbitrarily large. We had only 3 photons because of practical experimental issues, because otherwise we wouldn't have had a good signal to noise ratio in reading our results. But anyway, if you have n of these qubits in the homogenization machine, you do n subsequent partial swaps, and at the end of the sequence, you have a very high probability that the state of your initial qubit has been swapped with the state of the qubits in the homogenization machine. They all share the same state. That is essentially the goal state of your transformation.
So is it fair to say that the quantum homogenizer in constructor theoretic language, that is the constructor, and then the photons, which are serving as the qubits, those are the inputs that you're looking to transform? Is that correct?
It is correct for actual transformations that are considered possible in constructor theory. What we want to demonstrate is that some transformations in the constructor theory framework are possible and some are not. Essentially, in this particular case, the one-way transformation is possible and the reverse is not. Why? Because a transformation is called possible if there is a constructor associated to it that is able to perform the transformation. And what we wanted to demonstrate is exactly this, that the homogenization machine that exists for both the direct transformation and the direct task and the reverse one, in one case, in the direct task, qualifies as a constructor, and in the reverse case, it does not. It does not satisfy all the constraints, all the requirements for it to be a constructor. And so a non-existing constructor implies a not allowed transformation, let's say. That's exactly, at microscopic scale, you have reversibility, but the reverse transformation at microscopic scale does not imply that there is a reverse transformation at the macroscopic scale. That is essentially the core of our paper.
And to add something also, the fact that a transformation is possible, as Fabrizio said, implies that a constructor exists, but it also has to be able to perform the task repeatedly without degrading and with infinite precision, let's say, on an arbitrary small precision.
Right. So Laura, on that point, in your particular experiment, tell me the role that transforming qubits from mixed states to pure states and also pure states to mixed states. What role do those transformations play in your particular experiment?
Those are exactly the transformations we want to study. The task we are studying is going from a pure state into a mixed state, and the reverse task is therefore going from a mixed state into a pure state. In particular, what we measure is the precision with which the machine, or the error, let's say, the machine performs each task, the task going from pure to mixed, or its inverse task. And also we see how does the machine degrade every time the task is performed in one way or in the other. With these two quantities is that we can evaluate if the constructor qualifies, or if let's say the quantum homogenizer qualifies as a constructor for performing the task in one way and in the other.
So which of those transformations, pure to mixed or mixed to pure, turns out to be possible in the long run such that the quantum homogenizer does not break down, and which of those seems to be impossible, again, in the sense that the constructor does break down?
The answer is pure to mixed is allowed, and mixed to pure purification is not spontaneous. And that happens if you observe a figure. Essentially, all our test is based on a figure of merit, the relative deterioration of the machine that is to be determined if it qualifies as a constructor or not. And this relative deterioration for a constructor should go to zero. It's essentially the ratio between the error of the machine in performing the task divided by the resiliency of the machine when used for multiple tasks. And for multiple tasks, I mean, I have a certain substrate qubit with initially pure state. For example, I am dealing with the pure to mixed case, and I have my machine. It transforms the qubit one, substrate one, into the mixed state, and then I take a fresh qubit in the pure state again, and I take the same machine as before. That of course underwent some changes because the interaction make the machine change, and let's see how resilient it is to these changes. If you evaluate the ratio between the error and this resilience, you obtain the relative deterioration, and you can state that okay, aside being able to carry on task with arbitrary precision, so epsilon has to go to zero. In the limit of a large number of qubits in the homogenizer, let's say infinite qubits, and in the limit of an infinite number of usages of the same machine, anyway, the relative deterioration must go to zero. That means that the machine, to be a constructor, must retain and keep the ability, even if degraded, to carry the task with wanted precision. And essentially what we did in our experiment is really make our photons simulate this kind of interaction. And from the collected data, we evaluated, we reconstructed the state of the qubit to be transformed and of the machine at the different stages of the transformation. And then we evaluated those figures of merit, and we can see that, okay, of course, we can see it only for a number of n qubit equal to 3. That is quite far from the infinite, but we unfortunately, experiment and theory don't get along that much in that sense. In theory, you can always put things to infinity. It's very elegant and beautiful. I'm so jealous of it. In experiment, I mean, we're somehow very, very specialized mechanics, but we're still mechanics. And so we have to deal with finite stuff. And even adding a fourth or fifth qubit to our experiment would have meant risking to have inconclusive results. But anyway, from our paper, you can see that the first 3 points that we obtained for the curves, for the different transformations, for the curves of the relative deterioration, of course, really, really get along very well with the theoretical predictions. And the theoretical predictions really seem to go to zero for one homogenizer, and it explodes for the other one. And of course, it explodes for the mixed to pure homogenizer. And that means that the mixed to pure homogenizer is not a constructor. And that's why that transformation is not possible. That's why we have demonstrated, let's say, irreversibility as defined within the constructor theory context.
Got it. So in this case, the quantity that's very important is basically the degree to which the quantum homogenizer, which again, in this case is the constructor, breaks down in its ability to cause a transformation one way that the reverse transformation, namely pure to mixed quantum homogenizer, does not break down.
Exactly.
Perfect.
So let's talk a little bit more about the quantum homogenizer, because I imagine a lot of people are not very familiar with what exactly it is, what its purpose is. So Laura, could you please explain in layman's terms, what exactly is a quantum homogenizer and what's it used for?
Well, essentially a quantum homogenizer is, we can think of it as a machine which is composed of an arbitrary number of qubits, which act as what we call the rest qubits. And you have a system that basically interacts with each one of these qubits in the rest, eventually transforming the state of the system or of the substrate, as we call it in our paper, into the same state, which are all the qubits in this rest of the machine. So basically, it can perform, let's say, a transformation of the substrate qubit.
And Fabrizio, I want to talk about the actual experimentation process now. So walk me through and take as much time as you need in literally how you physically went about conducting this experiment.
Okay, well, first of all, I have to say that the actual experiment lasted not long, really, really not long. Why? Because unfortunately, here in Italy, as soon as Laura arrived here, let's say a couple of weeks later, we had the lockdown for the COVID, because it was 2020. When we were closed, we were at 1 day, you remember, 1 day or a couple of days from the acquisition, because we already had the single photon source up. Actually, the single photon source was up because we didn't do it from scratch, since it was my little single photon daughter that I realized for a few years ago. Well, not few, because I realized it about 10 years ago. And it is a specific prototype of a single photon source that is a beautiful one, essentially, because it's a heralded single photon source that has the beauty that not to rely on post-selection. It's excellent for telecom, for fiber optics, because it's telecom wavelength, and that was basically ready. We did just some adjustments and some realignment of the equipment, of course, because it lay dormant for quite a while. But anyway, we were already testing the equipment just to mount the rest of the setup, the switch and everything, when we got closed. And so since we didn't want to bore ourselves, we passed the time to simulate some data elaboration, because the data elaboration was something completely new to us. We didn't know how to do that, because the partial swap is a very difficult gate to implement, especially in post-processing, as we did it. Actually, Laura did it. I just took credit for that, because we shared the tasks, and essentially she did the work, and I took credit for that, because okay, I can't do everything, you know. But anyway, after we were able to come back to the lab, in 1 week we managed to test all the equipment and calibrate everything, and then We took our single photon source, we analyzed its output, we connected it to the switch. It's a 1x4 switch. It's just a switch that essentially addresses electronically your photon to 4 different channels. One of these channels was the so-called substrate channel. The substrate is the qubit that undergoes the transformation in our model. And the other 3 channels are the reservoir channels that mean that they are addressed to the qubits forming the homogenization machine. So we have a 3 qubits homogenization machine. And then you have these 4 channels that get connected in a sequence of fiber beam splitters. Fiber beam splitters with different ratios, because we simulated a quantum homogenizer with different intensities. So we have the classical 50-50 beam splitter, that means 50%, 50%. Then we had the 25%, 75%, and the 10%, 90%. Of course, the 199 would have been impossible to deal with, because it would mean not having signal in some channels. Each single beam splitter took care of one of the swaps, of the partial swaps, actually, of the interaction between one substrate, and one of the homogenizer qubits. That means that you have the first beam splitter connecting the 2 channels, and essentially you have the substrate photon go to one of these beam splitters, and one of the reservoir photons also in the other side. You have this partial swap. Then what comes out on the substrate channel is connected to another beam splitter, and what goes out from that beam splitter is connected to another one, and then sensed and then addressed to our single photon detectors. And that's the substrate path. But you also have the other outputs of the beam splitter connected to this to the substrate and the homogenizer, and the other outputs are also detected by single photon detectors in the infrared, and they allow us to reconstruct deterioration of the homogenizer and the state of the homogenizer at all the steps of the interaction. We not only observe the status of the machine and of the substrate qubit at the output of all the sequence, but we can also do some reconstruction step by step, showing also how the transformation is carried by our homogenizer. This would not be enough, actually, to have the partial swap, because we have to add some post-processing in that. So we detect these photons with our detectors. The detected photons then go to some time tagging electronics, because we needed to observe some temporal differences, because our qubits are time beam qubits, not polarization qubits, because we cannot trust polarization in fibers unless we do very tricky stuff. But we didn't need to do that, so we switched to time beam qubits. That means that the 0 has a difference between the 1 that is dictated by some delay in time between the 2, not anymore. But anyway, as I was telling, there is some post-processing needed for actually be sure that we implemented the partial swap gate and not some other gate or swap, or some particular swap, or stochastic swap or something.
So as Fabrizio said, we have our machine, our homogenization machine is a 3 qubit machine, and we have also the substrate cubic. So at the end, what we have is 4 detectors, let's say 4 outputs of our machine, which consist of this cascade of fiber beam splitters that Fabrizio was mentioning before. And what we want to do is basically on each one of these fiber beam splitters, it's where the interaction takes place, the partial swap, or let's say not the partial swap until we do the post-processing, but it's the physical object that performs this operation that we are interested in implementing. So to basically be sure that the operation implemented is a partial swap, what we have to do is at the end of the whole process, select only the cases when all 4 detectors have clicked, so that all 4 detectors have detected a photon at the same time, or at least in a certain time window. we have lots of data on each detector with each one, with the time each photon has arrived. So we have to do basically a selection of every time each detector has clicked within the same time frame another detector has clicked before. And we only get information from those events and discard any other event when the detectors maybe clicked only 2 of them and nothing was received in other 2 of them, or when all photons go to only 1 detector, and so on.
Yeah, unfortunately, this means discarding a lot of data. So we had to collect data for a lot of time, especially one day. One day was terrible because we didn't collect anything. Even though we did very short acquisitions, about 10 minutes or 15 minutes or something, it's not that much in these cases. And we piled them up, of course, in post-processing. But that day we were not even able to make the equipment last that long in working properly. So we just surrendered. But anyway, in slightly more than a week, the collection part was done. And in a couple of weeks before, everything else was okay, because we did so much work before that we arrived basically ready to do everything. Actually, we did so much stuff more than what is on the paper that we could even write another one. All the details in additional material probably would have been 10 pages or 15 pages or so.
Yes.
It's interesting that the data collection portion of the experiment, is it correct that only lasted a week?
Yes, 9 days probably,
Yes.
8 to 9 days. But the data collection in quantum optics experiments is usually the tip of the iceberg. Sometimes it happened to me in previous experiment that lasted, for example, a couple of weeks, and the optimization of the system 1 year, or that is the difficult part. And sometimes it can even be reversed. You can mount the system and discover that although your system is optimized, the sensitivity of your setup to environmental conditions or temperatures or fluctuations or whatever do not allow you to really trust every single acquisition, and you have to repeat it because there are so many things that can go wrong. That's almost like tossing a coin with 1,000 faces.
No, and in our case, we have, let's say, we had 5 different configurations corresponding to 5 different partial swap probabilities. And basically, we had like 1 day to make the acquisition for each one of these configurations. We did wrong. I actually did wrong one connection 1 day. So that's why we probably took 2 more days to do the experiment. But
and there was also the day that nothing worked.
Yes. But if not, it was probably a day of acquisition for each partial swap probability that we were trying to test.
Slightly more sometimes, a day and 1 hour, maybe. That's why it took 8 days.
Do you anticipate using the quantum homogenizer in future experiments as they would pertain to constructor theory, or do you think probably not?
I don't know. Quantum homogenizer can still be used, and there's still room to study different processes. But I think also it would be interesting to study different machines within this constructor theory.
Well, the constructor theory is so much wider than the way that what we did. That's I'm not titled to talk about that because Chiara and Vlatko are much above me in this sense, and they know much more. But what I feel is that in our particular case, the constructor, the homogenizer was a toy model to say, okay, let's see how it could work in a toy model, and let's provide experimental evidence of this model at work, just to help visualize it, to help understand it in a deeper way. Because
and it was also a good, let's say, thermodynamic model to study because of this fact that we have a substrate that gradually interacts with the rest of the qubits and tends to go to the state of the machine.
That's what happens with the thermalization usually. So it's a sensible choice, of course. And quantum homogenizer is not a novelty that we introduced, was already there and implemented it in a novel way, actually. But anyway, it's definitely a useful tool for quantum information, and even quantum foundation protocols could be. But honestly, what puzzles me the most is that we didn't even finish to analyze all the data we took. So it probably will be used for something else, but the experiment would be the same or a little variation of this one. I really have the impression that we just began to scratch the surface of what we could do with this. It's a fantastic sensation, but I'd like to pursue this direction even more.
Laura, so Fabrizio was saying how this is very exciting. I wonder what exactly about these experiments having to do with irreversibility are so novel, given that there have been experiments having to do with irreversibility in physics in the past.
Let's say that the novelty is actually on the constructor theory, on the framework that was developed by Chiara and Vlatko and David Deutsch. The thing is, as Fabrizio mentioned at the beginning of the interview, we are trying to test, let's say, when a task is possible, we can say a constructor exists to perform it with infinite precision and without degrading, etc. And if the inverse task is not possible, there's no constructor capable of performing it. The thing is that in this toy model we are using the quantum homogenizer, this partial swap operation that we described before, it's what we call a unitary operator. It's a unitary operation which makes it basically reversible. So in theory, microscopically, let's say quantum theory, this operation is reversible. You can go from one way to the other just by reversing the operation. There's no problem. It's a time reversal. Everything is symmetrical in that sense. But using constructor theory, what we see is that it's not at the end. The operation, the task is not reversible. Therefore, trying to reconcile this concept of microscopic irreversibility with macroscopic irreversibility.
Right. So this goes to the point that really even all experiments are theory laden, that no experiment occurs in a vacuum. Fabrizio and Laura, I really appreciate your time. This was very illuminating. Thank you both very much.
Thank you, Logan.
Thank you.
Thank you to Fabrizio Piacentini and Laura Knoll for speaking with Logan Chipkin. I'm adding a link to their paper, Emergence of Constructor-Based Irreversibility in Quantum Systems, Theory and Experiment, on the podcast page, fqxi.org/community/podcast. There you'll also find links to previous episodes in this series, featuring Logan's in-depth interviews with Chiara Marletto, Vlatko Vedral, and Paul Davis. You can also check out episodes of the regular podcast from the Foundational Questions Institute, exploring the edge of reality. You can subscribe to the podcast on Apple Podcasts or Spotify direct on that page, so you don't miss out on upcoming conversations in the series, including one with David Deutsch coming soon. That's all we have time for today. You can find me on Twitter at FQXi and Logan at ChipkinLogan, and you can follow FQXi on Facebook, Instagram and Pinterest at FQXi Physics, and at FQXi on LinkedIn, or email us at podcast@fqxi.org. Thank you for listening. I've been Zia Morali.